Hey, what's up everyone? Welcome back. For those of you who are new to the channel, you might want to go ahead and check out our last video where I covered algebraic data types. This video we're going to go ahead and jump into talking about type classes. So while ADTs cover the different data types, type classes cover the behavior of how we can combine or manipulate those values within those data types. You can think of type classes as interfaces with generic function definitions, and that is without specific implementation. The idea here is that they loosely define polymorphic behavior, which is the ability to pass in generic values by way of abstraction. So you have these function definitions or these function signatures without implementing the actual logic of how the input should transform into a new output. The value add here whenever it comes to dealing with type classes is that we get this wealth of inherited functionality, these functions that are mathematically sound algorithms. And these algorithms provide us a way for not just manipulating data, the way that you would reduce a collection from a type A to a B, but it also gives us a way of orchestrating operations. And I want to explain that as plainly as possible because the value add is tremendous in the composition that it yields us. So depending upon the type class that you use, that orchestration or composition of functions can be either sequential or parallel. And this is going to make more sense as we look at a couple slides I have to show you, and then we walk through the code. Alright, now before we look at any code or any slides, I just wanted to go ahead and say up front that this video is going to be a long one, but rather than dumping an entire 40-minute video on you, I went ahead and cut it up into two parts. So this is the first one, and then the next one will be the final portion of wrapping up on type classes. So without further ado, let's go ahead and jump right into the technical deep dive. Okay, what we're looking at here is a diagram of different type classes. There's certainly more that exists than what's represented here, but for this video series, for the most part, we're going to focus on these right here. And for today's video, I'm going to cover Functor, a little bit of apply, Applicative, and another one called chain, which isn't represented here. Now, like I mentioned before, each of these type classes have very specific functionality that they offer. And that functionality is supposed to abide by certain mathematical laws that help us compose these functions in our application. We're going to start by taking a closer look at what the Functor type class is. Now, the Functor type class gives us the ability to map something from an A to a B. That could be an integer to a string, it could be an integer to an integer, whether you're incrementing the value, decrementing the value, it doesn't really matter. And honestly, the data type itself doesn't even matter so long as we have the capability of mapping the underlying value. So here we're saying that whenever we map something, we're transforming wrapped data that is produced by an effect, where the effect is the function that we give map. So again, the Functor type class has a map method on it. Now some of you might be thinking, that sounds a lot like, mapping values in an array. And indeed, your intuition serves you well. So let's go ahead and look at an example of that, where we take these two strings, Jack and Jill, and then we map over them and we provide this effect within the map that says what to do. How do we want to transform these values from A to B? A being the simple string that they came into as, B being a capitalized string. So it's still a transformation even though the data type remains the same. Let's move on to chain and explain what's happening there. So I'm going to get rid of this example, and I'm going to bring up some borders to give a separation of these definitions. And then we'll take a look at chain. Chain gives us the ability to compose a sequence of computations from an A to a wrapped B, using the return of one computation to determine the next computation. Now, let me take a beat there and explain what we mean by wrapped. We know that algebraic data types can implement these different types of type classes, like Functor and like chain. And whenever you hear me talk about wrapped data or wrapped operations, I'm talking about lifting those operations and data into these ADTs, which kind of make them smarter in the sense that instead of standing alone by themselves as a function or a data type, we actually gain more by lifting them into these ADTs. And the purpose of this series is to help you understand what you gain by doing all this. So don't worry if it doesn't make sense all at once. It might even take some replays to really start to get it. But if I'm doing my job right, then as we make progress, things will start to click and you'll pick up what's really going on behind the scenes. Now, just like with the Functor type class, where we said You know, the definition of mapping something from A to B sounds and looks a lot like the native implementation in JavaScript, where we can map on elements of an array. The same can be said for chain, where the similarity here is with flat map, because what we're actually doing with chain is unnesting a nested structure so that we can operate on the values within and repackage them into one level. Let's go ahead and take a look at an example to kind of jog your memory of what's going on with flat map. So we have an array here of strings, and in the second step of our procedure, we want to split on each element. And what this creates is this nested structure where we have an array of arrays. So we can pull in flat map to unnest that structure so we have a single array with the elements within. Okay, let me go ahead and get rid of this example so I can free up some space here at the bottom. The last type class that we're going to cover here is the applicative type class. Now, before I go into the definition or describe kind of what it buys us, I just want to say at a high level that this is a bit more advanced. And the purpose of me showing you this up front is because I know as a newcomer or a beginner to the paradigm that you're always wondering, like, what is the big value add here, and why are we learning all this? When would I pull it in? So the idea is to show you some high level feature sets that really buy you a lot in terms of composition, and like we've mentioned before, many of times this is going to elevate your ability to problem solve. Okay, so with that disclaimer out of the way, let's go ahead and take a look at what it gives us. So it gives us the ability to apply a wrapped function to a wrapped value, and it supports both sequential and parallel composition. Now, on the surface level, this isn't going to mean a lot to you until we look at the code. So we're going to go ahead and dive into some types next, and then we'll look at some test coverage that I've written for these different type class implementations. Now, before we jump into my code editor, let me do a quick plug here and say that the library we're going to be using throughout this series is FPTS, which, as it states here, provides developers with popular patterns and reliable abstractions from typed functional languages into TypeScript. And if we just drill down here and we take a look at type classes, it says that they provide the theoretical underpinnings of FPTS, and they described what you can do with your data to guarantee that they can safely be composed. And they are built on laws rooted in abstract algebra and category theory. So I just gave you a brief explanation of what functors are, what chain is, and what applicative type class does. And now we're going to go into my code editor where I've loosely defined these types and interfaces so we can look at that before we jump into actual business logic and see what we do with these methods. Alright, just a quick note in case you're new to TypeScript. In our last video, we touched on ADTs, and whenever we were looking at the type definitions, we used types for defining these different ADTs, where here we're looking at interfaces. And the difference is we use types to define what a data structure looks like, and we use interfaces to define what the behavior should be whenever implementing these interfaces. Okay, so what I've done to make this easier to follow along is I've plucked out these interfaces and these definitions from FPTS. And if you want to look for it yourself, there'll be a link in the description, but essentially you can come to modules, and for instance, you can go down to option, so options in ADT, and then here are the different type classes that it has implemented. And the one that we're going to start off with is Functor and what that map looks like. So we'll jump back over here, and now we can look at what the map looks like. So we have these generics right here where we have an f of a, and then we have a function where it's an a to a b. Now, whenever you see these HKT, that's FPTS's fancy way of building up these type constructors. So we could look at this definition up here to explain it. HKT stands for higher-kinded type, and it's FPTS's way of representing a generic type constructor. So when you see HKT with the F and the X, you can think of it as a type constructor where F is applied to the type X. So if we look again at our mapping here, you can see that the basic example says that map means foo of A and A to B will give us foo of B. So this portion right here where we have the A and the B up front is what's known as parametric polymorphism, which is a fancy way of saying that we're using generics to roughly describe the polymorphic behavior of this map function. And polymorphic, in case you're not aware of, is just meaning like whatever value we put in. Like mentioned before, we don't really care about the data type. What we care about is the transformation process. And here what we care about is transforming the A to a B within the context of its type constructor. And in the example here, that's foo. But that could be anything. That could be option, it can be either, etc. For each interface covered in this file, I have the mathematical laws associated with that type class, but for the sake of not throwing too much at you up front, we're just going to ignore the math laws here. But if you're curious, you can pull down the repository and check out these laws for yourself. Okay, now we're going to make our way down to the next type class, which is apply. Now I'm going to jump back to that diagram that I showed earlier because it's important to note here that applicative is an extension of apply. And again, chain is as well, even though it's not represented here in this diagram. Okay, now looking at this interface apply, you can see that we have this app method, and it gives us this ability to lift an operation from A to B into the algebraic data type. For example, an operation that transforms data, lifting that into an option. And then you also see that it takes an f of A, so this foo of A, which could be just a regular value also lifted up into that context as well. You'll notice that we have two examples underneath this app method that I've provided. You have the foo of A to B and a foo of A, which ultimately gives you a foo of B. And then right underneath that, I think this is probably a little more easier to follow along. And even if it doesn't make sense now, it will whenever we look at some code later on in the video. But that one shows you that you have a foo of A and a foo of B, which ultimately gives you this foo with both of those A and B's nested within. Okay, let's make our way down this file and look at the chain interface. And you can see here that it extends apply and it has a chain method on it, which takes an f of A and it takes a function that has a regular A and it transforms it into a foo of B. And ultimately that gives us a foo of B. Now again, this probably doesn't make much sense if you're just looking at the signature for the first time. It seems a little convoluted, but it will begin to be a little more clear whenever we look at the code. Okay, now the last stop for this file, we're going to take a look at the applicative interface. And this too extends apply. So in addition to apply's app method, we also have this method called of, and it's actually the simpler of the signatures here. To understand what's going on, simply it's just taking a value and it's putting that value into the algebraic data type. Here the example is A to foo of A, which could be a string to an option of string. Now it's time to move on from these signatures and the theory of everything and really look at some practical examples to hopefully give you a better idea of how you can leverage these things to your advantage. We're going to take a look at some example tests that I've written. So up at the top, we're importing expect from chai, which is just our underlying testing framework. And then you can see that we're pulling in apply, an option from fpts, and then we have some shared types. So in the last video, we covered this user type and what was going on there. And in this example, I'm just extending that definition and adding account balance and an optional data field called favorite quote. And for our tests down below, I've set up these two dummy profiles where we have a John Doe and a Jane Doe. And one of them has a favorite quote while the other one doesn't. I just realized that I gave them both the same ID. Let's go ahead and switch that up. Not that it really matters, but anyways. So we're gonna move down here and look at the first option test that we have written. So we say that an option can map values via its functor implementation. And you can see that by way of this pipe that we have. Right in here, we have this o.map, and then here's our transformation function. All right, and just a quick callback here. So like I said in the test, it can map values via its functor implementation. We're working with the option data type, and that is just aliased as O here. And I'm gonna go ahead and pull back up the example that I had over here, where in FPTS you can see that the option ADT has this map available to it via its functor implementation. I just want to make sure that I'm hitting on all those points so that you understand where these methods are coming from. Let me go ahead and move my terminal over to the right so you can see what happens whenever we run these tests. Okay, we're going to go ahead and start by running the tests. Alright, now you can see the first one is failing. And why is it failing? It's because we have the wrong expected value here. So whenever we map, we're saying, given that this user option, which is a sum of John Doe, which we've looked at up here, has this information, we want to map over that value and we want to pull out the account balance and we want to add 100 pennies to it. And we're saying that we expect that to be equal to an option of sum that contains, what is it, 30,000 pennies. So over here we can just go ahead and take what the actual value is, plug that back in, save it, and then we'll rerun our tests and see that hopefully we're passing. And there you have it. All right, another thing to touch on here, you see this pipe method that I have on line 39? You're gonna see that a lot throughout this series. And pipe is a way of composing functions from left to right. So the first function or value in there is gonna feed into the next function and so forth and so on. So whatever this is, which is an option of a user's profile, it's going to feed that into right here, which is actually the same as if we just did this. That's still going to run how we expect, and let's just go ahead and save it and yarn tests. Let's run that, and you can see that it still passes. Now it's freaking out right here because we've explicitly piped it in. It's missing that type inference. So we'd have to like manually come in here and say that it's a user profile, but we're not gonna do that. We're just gonna go back to how it was, because this is the beauty of point-free composition. And all that means is that if you have a function that takes a single argument, you don't need to explicitly call out that function takes that value into the end. It's automatically curried. And currying is whenever you do something like this. So let's say that we have a function called add it up, and it takes a number, and then it expects another number, and then finally it takes that x and it takes that y and it adds them up together, and you get this added up. Now, whenever you call this, you could do it like this, and that would provide us the value 5. Or what you could do is have a pipe where you have, let's say, a starting value of 2, and then we have added up, and in here we'll have the 5. And then this, we have a 3. And then this will also produce the same thing, because it takes this x and it feeds it in right here. So that's just what currying means. Whenever you write a function that expects multiple arguments, but instead of passing them all in at the same time, you partially apply it along the way. All right, now because we're starting to run long on time here and I don't want to dump a 40-minute video on you with information overload, we're gonna go ahead and take a break and pause now. And then I will see you guys in the next video where we pick up right where we left off. All right, everyone, thank you for joining, and I will see you again in the next video.